Ish. Okay, so hello everyone, good morning, especially in London, and we're happy to have Mira Shamis, and Mira will speak about, I forgot the exact title, so I think she will speak about shredding your operators. Don't run away. She's going to explain it to us.
The title is actually one of the most beautiful things about this work.
Yes.
First of all, thank you very much for inviting me. And the title, I must say what the title is, on the abominable properties of the Almost Mathieu operator with the Liouville frequencies. So and the operative word here is the abominable. So this is the word in which we will concentrate for this whole talk. So this talk is based on a joint work with Arthur Avila, Yoram Last, and Kijou, and it's already on the archive.
In the archive with the same title?
Yes, on the abominable properties of the Almost Mathieu operator with Liouville frequency. Maybe not Liouville, maybe with well approximated frequencies. I forgot what we decided.
The abominable properties, though. Okay.
Yes. That's the most important part. In this work, we study the Almost Mathieu operator, that is one-dimensional, discrete Schrödinger operator that acts on little L2 of Z by H, alpha, lambda, theta, psi of n equals to psi n plus 1 plus psi n minus 1, the so-called free discrete Laplacian, plus 2 lambda cosine 2 pi alpha n plus theta psi of n, where lambda is some real number called the coupling constant, about which you can think as the strength of the disorder. And we can always assume that lambda is positive, since negative lambda is simply a translation of theta by pi. Alpha is a number between 0 and 1, and theta is between 0 and 2 pi. And one can easily see that if alpha is rational number, some rational number p over q, then the operator is periodic of period q. And if alpha is irrational number, then the operator is what it's called almost periodic. And sometimes it's called quasi-periodic, and sometimes it's called one frequency operator. It depends on who's the author that you read. Now, it is well known today that the spectral properties of the Almost Mathieu operator depends very sensitively on the arithmetic properties of the frequency of alpha. So, for example, back in 1976, Gordon proved that any Schrödinger operator, which is well approximated by periodic operators, can only have continuous spectrum, only. Using this result, 6 years later, Abron and Simon proved that in the regime that lambda is greater than 1, which is the so-called supercritical regime, the spectrum of the Almost Mathieu operator with well approximated frequencies, namely Liouville numbers, is purely singular continuous. Now, on the other hand, in the same regime, supercritical regime, when lambda is greater than 1, in 1999, Zhytomyrsky proved that for poorly approximated alphas, namely Diophantine alphas, the so-called Diophantine alphas, the spectrum is pure point for almost every theta with exponentially decaying eigenfunctions.
What do you mean Diophantine, poorly approximated? You mean the continued fraction is bounded?
Yes, basically, okay. Yes, but I will actually introduce a parameter in a second from which we will see what is the meaning here of the Liouville and Diophantine.
So neither Liouville nor Diophantine are generic, right? So far, the generics have not been dealt with, or you haven't talked about.
No, they're both actually generic.
Well,
Diophantine numbers are of full measure, and Liouville numbers is G delta dense, so it's generic. It's bare generic.
Yeah, in a different sense. But wait, bounded convergence for the continued fraction. That's not full measure. Full measure is
No. Just a second. That's what I said. I will give the precise definition of what I mean in the terms, in the language of continuous fractions in just 1 second.
Okay.
So, and this singular continuous versus pure point, these two things gave some sort of indication that there should be a phase transition in this regime. And now I'm coming to the definition of what is actually meant by Liouville or Diophantine. In 1994, Zhytomyrskaya introduced the following arithmetic parameter, which we will call beta of alpha, which is the lim sup when q tends to infinity of -1 over q, logarithm of minimum over p of the difference between alpha and p over q. And this can be rewritten as the lim sup when n tends to infinity of logarithm of qn plus 1 divided by qn, where pn over qn is the sequence of convergence of alpha namely the sequence that arises from the continuous fraction expansion. And this parameter, precisely, you can think of that parameter as an indicator whether alpha is poorly approximated by rationals or well approximated by rationals. And we will say that alpha is Diophantine if this parameter is equal to 0, and it is Liouville, well approximated by rationals, if this parameter is strictly positive. Does it answer your question?
Yeah, for sure. This is almost always 0. Yes.
Yes, exactly. And she made the following conjecture that the spectrum is purely singular continuous if lambda is between 1, including 1, and e to the beta of alpha, and it is pure point if lambda is greater than e to the beta of alpha. So this is only for the supercritical regime. And this conjecture was recently proved by Avila, Yu, and Zhu in 2017, and independently by Zhytomyrskaya and Yu in 2018. Okay, the purpose of our work is to show that some of the properties of the Almost Mathieu operator with well approximated frequencies, namely in the case that this parameter beta of alpha is strictly positive, Liouville numbers can be very miserable. And actually, they can be as poor as at all possible in the class of all discrete one-dimensional Schrödinger operators. Okay. Also, let me mention one quite important thing, that we work not only in the regime, in this regime, supercritical regime, when we have pure point spectrum, but our results are valid also for the so-called subcritical regime when lambda is strictly smaller than 1, when it is known that the spectrum is purely absolutely continuous, namely the nicest one. Now we focus on the following properties. Yes?
Can I just ask the super and subcriticality is respect to which kind of behavior? Is it blow up of solutions or something like this?
It's the phase transition between the absolutely continuous spectrum to the regime of pure point spectrum.
Okay, yes.
Now we focus on the following properties. First is the Hausdorff measure of the spectrum. Second is the regularity of the integrated density of states and of the Lyapunov exponent. And third, homogeneity and the Parvidon property of the spectrum. So those are three things about which I'm going to talk today. And I'm going to start with the Hausdorff measure of the spectrum. And in this case, so this is the first bullet. And in this case, I'm going to talk about the so-called critical case when lambda is equal to 1. Now, it is known today, and I'm going to state a very elegant and simply looking statement, which actually took more than 35 years to prove. We know that the spectrum is a contour set of zero Lebesgue measure. And therefore, the question about its fractal properties naturally arises. So back in 2016, together with Lust, we have proved that there exists a G delta dense set of frequencies for which the Hausdorff dimension of the spectrum of the critical Almost Mathieu operator is equal to 0. Now, we can reformulate this statement in the terms of the Hausdorff measure. And for that, let me remind you the definition. So for a given subset of Rk, we're going to define T Hausdorff measure of a K as follows. We're going to cover our set K by intervals of lengths at most epsilon, and we're going to sum up the T's powers of the lengths. Okay, and then we know one can prove that it's not really hard to prove that the Hausdorff dimension of the set is equal to 0 if and only if T Hausdorff measure of the set is 0 for any positive T. There are more examples of operators with 0 Hausdorff dimensional spectrum, and you can consult the paper, survey paper by Damanik and Hillman for these examples. This is a survey paper, so if you will look also in the references inside the paper, then you will see all the examples. Now, the natural question that we address is the following. Can we replace the T's power by a more refined scale of a gauge function? And for that, first, let me modify a bit this definition. And instead of looking at T's power, I'm going to look for a given function omega. I'm going to apply the function omega to the length instead of the T's power. Okay, and I will going to call it omega Hausdorff measure of a set. So omega Hausdorff measure of a set, sorry, I want to pass to purple. It's exactly the same thing when I'm replacing T's power by a given function omega. And everything else stays the same. And it turns out that in this case, the right scale is the following function, omega t of s, 1 over logarithm to the power t 1 over s, when t is positive. Okay. It is known, and I will talk about this point, what I'm going to write a bit more shortly. It is known today that for any one-dimensional discrete Schrödinger operator of the form Laplacian plus potential, omega 1 Hausdorff measure of its spectrum is strictly positive. Okay. And in our first result, we showed that this point, a very, very weak point, cannot be improved even for the Almost Mathieu operator. And when I'm saying even, I mean that this is one of the most simple looking, nicest operators in the class of all one-dimensional discrete Schrödinger operators. And moreover, this is the most studied operator. There is, as some people say, it's ridiculous how much it is known about the Almost Mathieu operator, and still there are many things which we don't know. So in our first theorem, we proved the following. So let S alpha 1 be the spectrum of the critical Almost Mathieu operator. Then first, if alpha...
Just sorry for just a sort of sideways interruption. Does theta ever matter? I mean, so far it hasn't played any role whatsoever, I think.
Once again?
Theta. You've mentioned the role of lambda and the role of alpha, but theta, the phase shift.
No, there is no. It matters in some delicate questions, which I will not address, but not in this type of questions.
So for us today, it's basically extra baggage. Okay.
Yes. It's not extra baggage, it's a given parameter. We do not play with that parameter. We do not, so none of the results that I'm going to present are affected by change of theta.
Okay.
So if alpha is a Liouvillean number, namely very well approximated by a rational number, then for any t greater than 2, omega t Hausdorff measure of the spectrum of the critical almost Mathieu operator is equal to 0. And this result applies to t greater than 2, and there is still a gap between t greater than 2 and omega 1. And in our next point, we show that we can actually go up to omega 1. So second, if omega is any non-decreasing function which is 0 at 0. Sometimes these functions are called gauge functions. Decaying faster than omega 1, then there exists a G delta dense set of frequencies for which omega Hausdorff measure of the spectrum of the critical almost Mathieu operator is equal to 0. So on this, in here we show that we can go literally up to omega 1, up to the worst case. So before I proceed any further, are there any questions about that? Okay. Now, this theorem is about the critical case, and one can claim that, okay, it's not really surprising because all kinds of very strange and bad things can happen in the critical case, not only for the almost Mathieu operator, but in general. Critical cases, we know, is always the strangest case. In our next results, we show that actually very abominable, strange things can happen for arbitrary lambda, which is not critical when we talk about well-approximated frequencies. And my second subject is the regularity of the integrated density of states. Now, let me first, once again, remind you the definition. We define the theta averaged integrated density of states as follows. We will denote it by curly n with subscripts alpha and lambda. And this is the limit when n tends to infinity, 1 over n, the average over theta, simply integral from 0 to 2 pi, of the number of the eigenvalues of the restricted operator to subset of z from 0 to n, which are smaller than e. And when alpha is irrational, not necessarily Liouville, but any irrational number, then this average can be actually erased and this limit can be replaced with a pointwise limit. Now, the question that we want to study is how continuous the integrated density of state is. And for that, we define a class. So for modulus of continuity, omega we define a class of uniformly continuous complex valued functions with the modulus of continuity majorated by omega. Now, a classical result in potential theory called a Forssmann's lemma shows that if a set has small Hausdorff measure, then it cannot support any regular measure. Namely, if the spectrum is small, then the integrated density of states is irregular. However, the opposite direction is not necessarily true. So a little bit more precisely, Forssmann's lemma says that the omega Hausdorff measure of a set is positive if and only if there exists a measure supported on that set, which is regular with precisely the same modulus of continuity omega. And this is a very, very classical result. And from that result, we get, this is from Forssmann's lemma, that a zero Hausdorff measure of the spectrum implies that the integrated density of states is not uniformly omega Hölder continuous for a given omega. Now, for example, for alphas from our work with Lust, the integrated density of states is not uniformly Hölder continuous for any positive exponent. Now, by result of Craig and Simon from 83, we know the following, that for any ergodic Schrödinger operator, the corresponding integrated density of states is always omega 1 Hölder continuous. And later, this was extended by Bourgain and Klein to non-ergodic setting. So we know that for any Schrödinger operator, the integrated density of states is always uniformly omega 1 Hölder continuous. And this actually, let me scroll up, this takes us back to that statement. And now we see indeed that this is immediately, in some sense, an immediate consequence of the fact that the integrated density of states is always uniformly omega 1 Hölder continuous. Now, this result is optimal in the following sense. Craig in 83 and also Gunn and Kruger in 2011 constructed examples of almost periodic operators for which it cannot be improved. Okay. Now, in our case, for example, what we know immediately, that our first theorem combined with Forssmann's lemma imply that log Hölder continuity is optimal in the critical case. Okay. Now, outside the critical case, when lambda is not equal to 1, such, in some sense, simple considerations do not work because the spectrum is a positive Lebesgue measure. So what do we know for arbitrary lambda? So for arbitrary positive lambda, it was pointed out by Vila and Zhitomerskaya in 2010 that for G delta dense set of alphas, the integrated density of states is not uniformly T-Holder continuous for any positive exponent. So it's not an explicit statement. It was a statement that there exists a bare generic set of alphas for which this holds. There is a completely 180-degree different picture for poorly approximated Diophantine alphas. In 2008, Avila, following the works of Goldstein and Schlag, Avila and Zhitomerskaya, and work of Bourgain, proved that if alpha is Diophantine, namely our parameter beta of alpha is equal to 0, then the corresponding integrated density of states is uniformly half-Holder continuous outside the critical case. Now, in our next theorem, we show that for Liouville alphas, for well-approximated frequencies, the log-Holder continuity is actually optimal for arbitrary lambda, not only for the critical case. So our second theorem is the following. So first, if alpha is between 2 beta over 3 lambda and 2 beta over 3, then the corresponding integrated density of states is not uniformly omega T-Holder continuous for any T greater than 3. Now, if we restrict a bit our assumption on lambda, then we can get something better. Now, if lambda is between e to the minus beta over 2, e to the beta over 2, then the corresponding integrated density of states is not uniformly omega T-Holder continuous for any T greater than 2. And once again, there is still a gap between that and omega 1. And then our last point, we show very similar to the Hausdorff measure that we can go up to omega 1. So 3, if we take similarly omega a gauge function, decaying faster than omega 1, then there exists then for any lambda not equal to 0, there exists a G delta dense set of alphas, of frequencies, such that the integrated density of states is not uniformly omega Hölder continuous. Now, to the best of our knowledge, those are the first explicit examples of Schrödinger operators with almost periodic potentials with such low regularity of the integrated density of states. And an interesting feature of our construction is that in the subcritical case, when lambda is smaller than 1, and it is known that the spectrum is purely absolutely continuous, as follows from the work of Avila and Damanik, the integrated density of states is also absolutely continuous. And this is quite strange. Now, for the next 2 minutes, if you do not know what the Lyapunov exponent is, then you can safely go to sleep and wake up in 2 minutes, because I'm going to make quite quick and short remark that these results imply very similar properties for the Lyapunov exponent. Now, the Lyapunov exponent connected to the integrated density of states by the famous formula, which is called the Thouless formula, which goes back to the work of Thouless, Herbert, and Jones, which gives a precise connection. Now, there is an argument of Goldstein and Schlag that connects the regularity of the integrated density of states with that of the Lyapunov exponent. Unfortunately, the argument in their paper does not formally cover our omega t's, so we needed to generalize it a bit. And after this generalization, we have the following statement, that for any t greater than 2, if the integrated density of states is not uniformly omega t Hölder continuous, then the corresponding Lyapunov exponent is not uniformly omega t plus 1 Hölder continuous. Therefore, all these results are valid also for the Lyapunov exponent if you increase t by 1. Are there any questions?
Mira, I had a question earlier in point number 3. You said that in the subcritical case, the spectrum is absolutely continuous. And then you said that your results imply that also the integrated density of states is absolutely continuous.
No. This follows from result of Avila and Damanik that the integrated density of states is absolutely continuous. We show that even though it's absolutely continuous, it's actually only log Hölder continuous.
All right.
So this combination is quite strange.
Yes. All right. Yeah. Okay. Thanks.
Now, our last result is motivated by the inverse spectral problem for quasi-periodic operators. I will not go into too many details here, but let me explain you what the problem is and what is in general going on. Now, the problem is the following. Given a compact subset of R, we're asking what are the spectral properties of all the Jacobi operators whose spectrum coincides with that compact set. Now, in 95 and 97, Sodin and Yuditsky studied this problem in the class of Jacobi operators with almost periodic potentials. And they proved that if the spectrum of a Jacobi operator is homogeneous, which is the property of a set, simply set, and the diagonal elements of the corresponding resolvent operator are purely imaginary on the spectrum, then the operator is almost periodic. To the best of our knowledge, these works and all the following works on the inverse spectral problem require either homogeneity of the spectrum, which means that it cannot be too meager near any point, or a weaker condition called the Paravidon property, which basically says that the space of analytic functions on the complement of that set is sufficiently rich. And then a very natural question arises. Does the homogeneity, or at least the weaker Paravidon property, hold for simple quasi-periodic operators, and in particular for the Almost Mathieu operator? And surprisingly, the answer is not always positive. Now, first, let me remind you the definition of a homogeneous in sense of Carlson set. So we say that a set is homogeneous if there exists epsilon naught and tau between 0 and 1, such that for any point in the set and any epsilon smaller than epsilon naught, it is not too meager around that point. Namely, the measure of the intersection of the set with the intervals centered at the point of length to epsilon is greater than or equal than tau times epsilon. And I will not define precisely the Paravidon property. Now, up until now, all the results that we are aware of.
Could you just write the property that you're not going to define? It's a little hard to hear exactly what you're saying.
The Paravidon property.
Okay, got it.
Which once again basically says that the space of analytic functions on the complement of the set is sufficiently rich. Now, up until now, all the results that we are aware of, for example, Damani, Goldstein, Schlag, Voda from 18, and Legal, Yu, Zhao, and Zhu from 17, dealt with poorly approximated alphas, namely the Diophantine alphas, and they show that in that case, the spectrum is homogeneous, and in particular, satisfies the Paravidon property, since it's much weaker property. Now, recently, Simon conjectured that the spectrum of the Almost Mathieu operator is homogeneous always outside the critical case for any lambda not equal to 1. We strongly disprove this conjecture and prove the following. If lambda is between e to the 2 beta of alpha over 3 and e to the minus 2 beta of alpha over 3, then the spectrum of the Almost Mathieu operator is not homogeneous. And second, if we restrict our assumption on lambda bit, namely, if lambda is between e to the beta of alpha over 3 and e to the minus beta of alpha over 3, then the spectrum of the Almost Mathieu operator does not satisfy the Paravidon property. And to the best of our knowledge, these are really the first examples of ergodic Schrödinger operators with a spectrum of a positive measure which is not homogeneous and does not even satisfy the power beta property. And these examples in particular imply that a solution to the inverse spectral problem, which would include the Almost Mathieu operator with these frequencies, may essentially require new methods. Okay, in the last 15 minutes, I would like to present a bit of technical details, but before that, are there any questions about the formulations of results as is? Okay, then I want to ask the organizer, how much time do I have? Do I have 15 minutes?
Yeah, I guess 15 minutes is it's a bit over, but you can take 15 minutes.
Okay, thank you. I will try to do it by less. So I would like to tell you very briefly, as much as 15 minutes allows me, about the key ideas and ingredients in the proof in the first part, in the proof of the first part of theorem 2. I'm reminding you that this said that if we have lambda between 2 beta alpha over 3 and e to the minus 2 beta alpha over 3, then the integrated density of states is not uniformly omega t Hölder continuous for any t greater than 3. Now, the main arguments are developed for the case, for this subcritical case actually, and then it's quite a standard in this whole game, and the arguments are extended by what is called the Reandra duality. Now, the proof is based on the periodic approximations of the almost Mathieu of the almost periodic operator by periodic ones. And in this case, we know that the spectrum does depend on theta. And for any fixed theta and fixed p over q, the spectrum consists of q bands. And the first thing that we show is that the lengths of these bands are not exponentially small on q.
Sorry, the length of what?
Of these bands.
Bands. Oh, yeah.
Now, as theta varies, these bands can move and their lengths can change. So we have that picture. So, and we prove that in our second thing, we prove that the edges of the bands are moving by a quantity of order lambda plus little of 1 of q. Okay. Now, these small intervals, which lie in the spectrum for some thetas, but do not lie in the spectrum for other thetas, are the main focus of our attention. Okay. Now, and the main idea of the proof is the following. Take one such interval, more precisely the middle part of this interval of half size of the interval. And then on the one hand, we show that if the difference between alpha and p over q is sufficiently small, then the integrated density of states admits the lower bound which is of order of lambda to the power q over 2 times up to little of 1. And this bound is actually consistent with the second part, since we know that the integrated density of state has a square root singularity at the edges. Now, on the other hand, we show that if alpha is well approximated by rationals, then the intersection of the spectrum of the almost periodic operator with this interval is very meager. Namely, for any regular measure mu, regular in the sense that mu of an interval of length epsilon is of order of constant over logarithm to the t1 over epsilon for t greater than 3, assigns little weight to it. Namely, it is bounded from above by lambda q over 2 times t minus 2 plus little of 1. And from logarithm. And from our lower bound, we see that the integrated density of states cannot admit this upper bound, and therefore it cannot be regular. And in the 5 minutes that are left, I would like to tell you two main ingredients in the proof of the lower bound and in the proof of the upper bound. And I will start with the upper bound, because if I will not have time for the lower bound, then that's okay. But for the upper bound, it will be a pity. The main technical proposition on which the upper bound is based is a strengthening and generalization of the main technical result from our work with last. And actually, it is also the main technical result in this work. And all the theorems rely on this technical result, and the proof of it takes more than a third of the paper. So I will formulate it in the notations of that talk. In the paper itself, it is formulated in a bit more general way. So we have the following proposition. So this is for the upper bound. Let us take lambda in the subcritical regime. Then for any positive r, there exists an integer that depends on r and alpha, such that the following holds. Assume that P over Q and P tilde over Q tilde are two rational numbers, such that, first of all, they're both very close to alpha. And second, Q tilde is much greater than Q, which is greater than or equal than Q naught. Then, for any point in this interval, that we took this half-size interval, which lies in these small intervals, which are in the spectrum for some theta and not in the spectrum for the other thetas. And for any epsilon greater than some very small number, the Lyapunov exponent that correspond to the periodic operator with period q tilde at the complexified energy E plus R epsilon admits precisely this bound that we wanted for the integrated density of states for any theta between 0 and 2 pi. This is the main technical proposition on which the theorems of all, on which the proofs of all the theorems are based. And this is the main thing in the proof of the upper bound. And since I do have 3 minutes, which I'm very happy about, let me tell you one main thing in the proof of the lower bound, in particular, because we think it's maybe of an independent interest. So the main thing in the lower bound is the following. First, we show that that lower bound for the integrated density of states, this lower bound, holds in the case that alpha is rational. And then also the theta averaged integrated density of states admits the same bound. And then the question is how we pass from the rational case to the irrational case, which means that we need some sort of statement of continuity of the integrated density of states as a function of alpha. And there is no such statement in the literature. So, and we proved it in the following quite general setup. So let us assume we have a quasi-periodic operator as before acting on L2 of Z as the free discrete Laplacian plus the potential. Where this function phi is the function, real valued function on the torus, which satisfies a uniform Lipschitz condition. Okay, and we will denote as usual curly n with subscript alpha the corresponding integrated density of states. Then we have the following proposition about the continuity of the integrated density of states. For any R alpha dash L greater than 1, if K is greater than or equal than 2 pi, the Lipschitz norm of phi times the distance between alpha and alpha dash times L, then the integrated density of states that corresponds to the operator with alpha dash at the point R is smaller than or equal than the integrated density of states that corresponds to the operator with alpha at the point R plus K plus a correction of order 1 over L. Namely, we have the continuity of the integrated density of states as a function of alpha, a very nice continuity. And this is for any general almost periodic Schrodinger operator, not necessarily for the almost Mathieu. This is the main thing in the lower bound. And now my time ran out, so I will stop here. Those are the main things that I wanted to say, and I will be happy to answer any questions.
Okay, thank you very much.
Thank you.
Any questions? We have time for maybe one or two quick questions.
I can go scroll up, down, whatever you wish.
Mira, so in the last proposition is then used when alpha and alpha prime are exponential equal e to the minus beta or something. What is the
No. Alpha and alpha prime will be exactly alpha as irrational alpha and approximate P over Q.
All right, I see.
So we will compare.
Yeah.
We want to say that whatever holds for the periodic case, the same thing will hold for the
Right.
almost periodic case. But for that, we need continuity with a nice error.
All right. Very good. I wanted also to ask, so is there anything left for the almost Mathieu operator?
Oh, there's a lot. First of all, unfortunately, and here I'm crying more than bragging, this result is not optimal. So when it comes to the regularity of the, so if you're asking me what's the optimal in my conjecture, for example, for this theorem, second theorem,
right?
I
Yeah.
would say that the optimal is exactly as in the proof of the conjecture of the phase transition in the spectrum. I would say that the optimal probably is lambda between e to the minus beta and e to the beta. Also, the same probably is optimal for the homogeneity. And here I come with the biggest cry of my life is that I have absolutely no idea what would be the optimal exponent for the failure of the power rhythm condition. That I simply don't know. So this is first. Second, there is a huge, it has nothing to do, no, it has a bit to do with this talk, but there is a huge open question. What is the Hausdorff measure of the spectrum of the critical almost Mathieu operator? And the best known result today, which
the Hausdorff measure, you mean at the gauge function omega 1?
No, I mean Hausdorff dimension. I said Hausdorff dimension. It wasn't a mistake. We don't know even about the Hausdorff dimension. So after 30 years of people thinking about that question, the biggest leap is today that Zhytomyrsky and Krasovsky proved that for any irrational alpha, it is smaller than or equal than half, which is a huge leap because up until their work, there wasn't even a proof that it's smaller than 1. But still, we do not know what is the Hausdorff dimension of the spectrum for a typical alpha. We don't. And moreover, there may be even different answers for different typical alphas. So this is another thing. Then there's a question about the behavior of the eigenfunctions in the critical case, which we don't know anything about. And I will not even start with the fact that we still don't know. Here comes the theta that Moshe asked before, where theta comes into the game. So, for example, we do know that the spectrum in the critical case lambda equals to 1 is purely singular continuous. And now I need to say, except for a discrete set of thetas where we do not know whether it's singular continuous or there is an embedded point spectrum. So and there are many other questions which are still hugely open. So even though this is the most studied operator, and even though lots of people, it's almost a quotation, saying that it's ridiculous how much it is known about the almost Mathieu operator, there are still many things that we do not know at all, not even ideas. For the Hausdorff dimension, for example, there is not even a proper conjecture.
All right, thanks.
Okay, so I think there are no more questions, so let's thank Mira again.
Thank you very much.
Thank you.
Thank you.